and Peter. So today I'm going to talk a little bit about some of my work on how we can start to build robotic learning systems for the real world. All right, so I'll leave questions for the end, but I'll leave some time for questions after I'm done. So at a high level, my goal has been to build continually improving learning systems. So what do I mean by this? Now, in a typical machine learning system, you start with a large data set, you employ a good learning algorithm, and then you have a model that you can deploy into a particular application. However, in the unstructured real world, this model might be far from perfect when it's deployed, and we might instead want to keep collecting data in the environment so that the model keeps getting better. So to this end, a continually improving learning system is one that can collect its own data and continue to improve its behavior as it gets more and more experience in the environment. So for instance, let's say you have a robot in somebody's home. The longer it spends in their home interacting with different elements of the environment, the better we want it to get. So the question really becomes, how do we go about building these types of continually improving learning systems?
So training a robot is very hard.
Ma-
So he's trying to make how to make it easier to train a
Sorry,
robot
one second.
so that
Can you mute
humans
it?
don't
Hello?
have to be involved.
God. Okay, sorry about that. Reinforcement learning provides us an elegant framework to do so. And reinforcement learning can most intuitively be understood as learning through repeated trial and error interaction with an environment, much as the way that a dog is trained by a positive reinforcement. So in RL, there's an agent which is perceiving the state of the world S and deciding what action to take A according to some set of decision rules, which we're going to call a policy or pi. Now, once chosen, this action is then executed in the environment and the world transitions to a new state, providing the agent a reward R in the process. Now, the goal of the agent in reinforcement learning is to utilize the repeated trial and error interactions with the environment to learn a policy that is able to maximize obtained rewards. So the interesting thing about RL is that we can directly train it via interaction in an environment without requiring a pre-provided model of the world. And doing so makes it quite straightforward in principle to acquire new skills and allows agents to continue improving their behavior at test time and continue collecting data to keep improving. So this sounds great in principle, but do these reinforcement learning algorithms even work in practice? So RL algorithms have been used with a lot of success in solving a variety of simulated problems, ranging from Atari games and video games like StarCraft to complex board games like Go, and even with success in the simulated character control community. So these successes were quite inspiring and made us think about whether these algorithms can have a transformative impact on problems with a more real world flavor. So problems such as robotics, dialogue generation, or automated tutoring systems, amongst many others. Today, I'm going to specifically focus in on the problem of robotics and discuss why I think RL is a really promising tool for robotics. Then we'll talk about what makes it challenging to actually apply reinforcement learning techniques to robotics problems and some ways we can go about resolving these challenges. All right, so a natural question to ask here is, why is reinforcement learning even a suitable choice for problems in robotics? So when we consider robotic deployment into unstructured environments, environments which naturally have a huge amount of diversity, variability, and complexity, so things like our homes, hospitals, or shopping malls, we want techniques that are able to effectively learn with a minimal amount of human effort and can continue improving their behavior with experience in these environments. So let's consider an example of a robot arm operating in a kitchen. Now, given this type of embodied system, we should just be able to drop a robot into these environments, indicate what behavior needs to be learned, and then allow it to learn these behaviors autonomously with reinforcement learning. So when applied in this way, RL provides an extremely promising tool for building robotic agents that can actually operate and learn in these unstructured environments. However, it's proven quite difficult to actually apply reinforcement learning in this kind of plug and play way for robotics problems in the real world. Instead, we've been limited to somewhat simplistic problems in very carefully designed environments and tasks, or limited to problems in simulation. So if you look at some of the works from our own groups, we can see that robotic RL has largely been limited to restrictive settings like moving an arm to a fixed position, contrived problems like pushing an object in the plane in a really restricted region, or tasks that require constant human intervention. Now, given that RL algorithms have been so successful in a variety of other domains, what makes it so much more difficult to apply them to the broader set of robotics problems? Now, looking at this problem a little more closely, it becomes clear that the challenge of building robotic learning systems with RL lies in the fact that there's a mismatch between the assumptions that most of these RL algorithms make as compared to what's actually available in the real world. So, to understand this, let's look at the difference between a domain where these algorithms are successful, like an Atari video game, and a robot learning in a real world kitchen. So in the Atari game, rewards are easily available in terms of the score. You can essentially collect an unlimited amount of data for free because you're in a simulated game, and you have complete control over the state of the game, which allows you to keep resetting and trying over and over again. However, in a real world robotic system, rewards are not clearly defined or provided. There's no score which is telling you how well you're doing. Robots are bound by their physical limitations to have a finite amount of experience, and you don't actually have oracle control over the state of the world to set it to whatever you'd like. Now, given that most reinforcement learning algorithms are critically reliant on these kinds of assumptions, it becomes hard to apply these algorithms as they currently stand to real world robotics problems in natural environments without significantly limiting or modifying these environments. At a more fundamental level, this mismatch lies in assumptions about how data is collected and utilized by these RL algorithms. So, what does data even mean in the context of reinforcement learning? So in RL, the agent is collecting its own data set via interaction with the environment, where the data set consists of tuples of states S, actions A, next states S prime, labeled with rewards R, and each action executed in the environment yields one of these tuples. This data set continues to grow as the agent interacts with the environment. For the sake of notation, let's denote the potentially non-stationary distribution that these tuples are drawn from by P and the number of samples in the data set as N. So, what I'm going to argue for in this talk is that the reason that the success of RL have largely been limited to video games or contrived lab settings can be attributed to the difficulty in actually obtaining the right types of data in terms of three factors. Firstly, it can be difficult to obtain the right supervision or the right reward function, R. Secondly, it can be difficult to ensure we collect data from the right distribution in an efficient and safe way or to get the right P. And lastly, it can be difficult to ensure that these systems scale up to collect enough data or get the right N. And so, what all of this boils down to is extremely simple. If you have a machine learning algorithm and it can't get the right data in real world environments, it doesn't really matter how good the optimizer is, you can't actually apply it to the problems you care about. So, today we're going to discuss how we can address these three challenges. How do we address the challenge of supervision, distributions, and autonomous data collection in order to actually ensure that these reinforcement learning algorithms are able to collect the right quality and quantity of data that they need to operate and scale in the real world under real world assumptions? So, a natural question to ask here is, are these challenges limited to just robotics problems, or are they more widely seen across a variety of decision making systems? So, these challenges about mismatched assumptions are common across a variety of real world problems, ranging from dialogue generation to healthcare to HVAC control and even educational systems. Essentially, any system where data collection and utilization has a non trivial cost is likely to see these problems of mismatched assumptions. I'm going to allude to some of these challenges throughout the rest of my talk as well, but for the large part, we're going to focus in on the robotics problem today. So, the rest of my talk is structured around how to tackle these three challenges. How do we provide the right supervision? How do we collect data from the right distributions? And how do we ensure large scale continual data collection in RL? By tackling these three challenges, we're going to be able to build robotic learning systems that can actually obtain the right data to operate and scale in the real world. Let's start by thinking about how we can actually supervise our real world learning systems. So, when I say supervision, the key question that is being asked is, where do rewards come from? So, the RL formulation assumes that when agents act in the world, the environment itself provides them rewards, somewhat magically. While this might be true in certain types of video games where the score is available, it's simply not the case in most real world environments like a robot arm operating in a kitchen. In these cases, reward must be explicitly provided by a human somehow or inferred by the agent from its own observations. And this becomes a fundamental problem. If the agent doesn't actually know what it's supposed to do, what does it optimize for? Right? So the typical pipeline that folks use for supervising a robotic RL system looks something as follows. A human user starts by setting up a state estimation system to understand where all the entities in the world are. For instance, a motion capture system or a pre-trained vision system to understand where the objects and obstacles in the world are. Then the user painstakingly designs a detailed reward function based on these state estimates, which can then be used for reinforcement learning. Now, the difficulty with this pipeline is that it's extremely hard to do in every environment that we encounter. State estimation is quite expensive to implement over and over, and reward function design requires considerable domain expertise. This whole pipeline requires several hours to implement for every new task and domain that we consider. And so, this requirement for reward provision is often what limits us to these limited task setups because they're easy to provide rewards in. It's more difficult to scale it to the broader class of robotic learning problems. So this led us to think, how can we go about reducing the cost of supervising these systems to provide rewards without all of the complexity? And the key here is to move from manually specified programmatic rewards to a more data-driven approach for reward design. So in a data-driven approach for reward design, a human user would easily provide some data indicating what the task is to be solved, and then the agent would infer rewards from this data and its own experience. So this might involve figuring out how to infer rewards from easy to provide source of supervision, like raw videos, or things like images of successful outcomes, or even more abstract forms of feedback like natural language. The key question to ask when considering data-driven reward design is, how do we actually interpret and utilize these extremely natural forms of supervision for scalable reward provision during learning? So let's think about this problem in more detail in the context of learning from raw videos. So the setting we're going to consider is thinking about how we can enable our robots to learn from raw videos of human experts performing a task. So as shown here, we can see that babies often employ this paradigm of imitation from observation to great effect, where they're able to extract reward supervision directly from raw videos of humans performing tasks, often in a very different scenario than their own. So we ask the question, can we enable our robots to do the same? Can we enable our robotic agents to infer reward supervision directly from raw videos of humans performing tasks, potentially in different scenarios than their own? To make this more concrete, the problem setting we care about is that we're given raw human demonstration videos demonstrating a particular task. Now, these demonstration videos are provided as sequences of images without any low-level states, actions, or rewards provided. Importantly, these can be provided in different contexts, including various viewpoints or camera angles, lighting, background, or even relative object positions. As seen from the video shown here, in this work, we largely consider variations in viewpoint, although the context can be defined more broadly. Now, the goal given these video demonstrations is then to infer a suitable reward function, which can guide the agent towards learning the specified task in a novel context. All right, so why is this problem difficult? This problem is difficult because firstly, the agent has to understand what is happening in the video directly from raw images in terms of the task being accomplished without having any access to low-level states, actions, or rewards. And secondly, the agent has to do this by reasoning across a variety of different viewpoints in doing so, which makes the problem significantly more challenging than traditional methods for learning from demonstrations or inverse RL. These would assume that demonstrations are provided with low-level states and actions, and in the embodiment of the system. Okay, so given this problem statement in mind, how can we actually utilize this type of video supervision? Intuitively, there are two key ideas we can leverage. Firstly, given a number of video demonstrations in a variety of different viewpoints and contexts, the agent needs to be able to visualize what the expert behavior would look like in its own context. And once the agent has visualized what the expert would have done in its own context, it then needs to try and match its own behavior to this visualized expert behavior. So how do we actually go about implementing this intuition? In order to predict what the optimal behavior looks like in the robot's context, this can be done by learning a pixel-level translation model that can translate frames from one viewpoint to another. By doing this type of translation, we can recontextualize behavior from one context to another, providing the potential to generalize to new scenarios that might be encountered by the robot. Intuitively, what this model allows us to do is to imagine what the expert would have done in the robot scenario. Now, once the context translation model has been trained offline, it's then relatively straightforward to provide reward functions for reinforcement learning. So given a new context, this context translation model is first queried to infer translated demonstration videos in this new context. And then the reward function can be to simply minimize the divergence between representative features of behaviors executed by the robot and the translated demonstration videos. So in this work, we specifically minimize divergences between intermediate features of the translation model extracted via an information bottleneck, although a more sophisticated feature extraction scheme could be used here. So this, in essence, just tries to make the robot behavior as similar as possible to the translated video demonstration behaviors. Okay, so putting these pieces together, the overall training pipeline looks something like this. We start off with a number of expert video demonstrations in a variety of different contexts. These videos are used for offline training of a context translation model that translates these behaviors between different contexts. Now, when the robot is encountering a new context, this translation model is queried first to predict the behavior in a new context, and then we can assign rewards via the simple feature matching objective that we just described. All right, so let's try and understand how well these ideas can work experimentally by first visualizing the video supervision that we use. So for three tasks, pushing an object to a location, ladling almonds into a saucepan, and sweeping almonds into a dustpan, we see a variety of videos provided by myself as well as a collaborator. So these videos indicate the general task to be solved while widely varying the viewpoint and lighting and to some extent the relative object positions and orientations. Now, given these types of raw videos, let's try and understand how well our algorithm can actually learn these robotic behaviors. So on these tasks, we can first visualize what the context translation model does. So we can see that it does something reasonable in terms of pixel space prediction for novel contexts, but it's often a bit blurry in its predictions. However, the important part is when you use this to extract reward functions for reinforcement learning and actually have an actual robot learn how to do these behaviors, you can actually learn behaviors like pushing an object or sweeping objects into a dustpan or ladling almonds into a saucepan, all without requiring any hand-provided reward function or any explicit state estimation or instrumentation in the environment. Now, this is particularly important for tasks with granular media, so tasks like sweeping or ladling, because actually instrumenting these tasks and providing reward functions can be extremely difficult, right? If you had to instrument something with almonds, you have to put a marker on every single almond or a tracker on each of these, and this can become extremely tedious. All right, so what does all of this serve to accomplish? Now, this was one of the first works that demonstrated the ability to go from programmatic rewards or even low-level demonstrations to directly supervising robotic learning from raw videos. Now, this serves to significantly reduce the amount of machinery and complexity of the supervision system, going from several hours of setup to just a few minutes. And this becomes especially important for hard-to-instrument tasks like manipulating granular media. However, it's important to acknowledge here that the demonstrations of this work have largely been on somewhat controlled videos and tasks. I think that going from here to truly unstructured video supervision in the future would require us to be more deliberate in our choice of feature representation, potentially benefiting from the use of ideas from computer vision like pose estimation, affordance learning, or image-to-image translation. And this might allow us to scale to using truly unstructured data sets like this for supervision. So some excellent work by many of my colleagues here and at other institutions have started to explore these directions, but I'd be pretty keen to explore this further in the future. So stepping back from the details of this particular work, we can take this concept of data-driven reward design a step further. In order to do so, I explored techniques for learning from static images of successful outcomes using success classifiers rather than requiring entire demonstrations. So this form of supervision is easier to provide while still being able to solve complex robotics tasks. We then considered incorporating more abstract forms of supervision like natural language feedback. So in doing so, we grounded natural language feedback such that it can be used to continue improving behaviors in new environments just by talking to your agents. And lastly, we took this to its logical extreme, exploring how to learn diverse skills without any reward functions, providing a general purpose framework for pre-training reinforcement learning agents without rewards. I won't have enough time to cover these papers in detail today, but I encourage you to go through these papers for a more comprehensive look at these techniques. So all in all, these techniques serve to make the point that we need to go beyond standard programmatic techniques for reward supervision and instead leverage data-driven techniques for reward design. This could include learning from raw videos, outcome examples, or even natural language feedback. Importantly, these techniques make it much easier for us to provide supervision without complex machinery and with minimal human effort in real-world environments, solving tasks like manipulating granular media. Now, these problems and techniques are ubiquitous, not just in robotics, but across domains like dialogue generation or educational systems, where reward supervision can be challenging to obtain. And I expect that moving to data driven reward provision techniques can have a significant impact in these domains as well. Okay, so revisiting our ingredients of a real world RL system, it becomes clear that in order to tackle the first challenge and provide these algorithms with the right supervision, we can build algorithms for data driven reward inference. Let's next consider our next challenge. How do we obtain data from the right distributions? So, in the notation introduced from earlier, the question of distributions becomes how hard is it to sample from the right distribution to learn complex tasks? Now, in reinforcement learning, the distribution of data is not actually fixed and is continuously changing according to the policy and the learning algorithm. So, this question really boils down to how easy is it to build reinforcement learning algorithms that can explore the environment to learn complex tasks in an efficient, safe, and practical way? So, for instance, let's say we want a robot arm to put a kettle on a stove. If it spends all of its time collecting data of states near the sink or dangerously hitting the cabinets rather than actual interaction data with the kettle, then the process of collecting the right data to learn how to manipulate the kettle is likely to be impractically slow and dangerous. So, to understand this challenge more concretely, let's consider the simulation and video game domains that we had talked about earlier. Learning tasks in these domains can often take several days of data collection, with data collection often involving unsafe interaction with the environment as shown here on the bottom. Now, in a video game or simulation, this data is effectively free, and efficiency or safety is not a major concern in the learning process. However, for a real world problem, such as a robot operating in the kitchen, real world data is not free. Robot experience is limited by its physical embodiment, and unsafe or very extensive interaction can be extremely costly for these learning agents. So these challenges are part of the reason that most RL algorithms have been limited to pretty simple settings like 2D pushing in the plane. If we want to actually go beyond these, we need reinforcement learning algorithms that can actually take the cost and difficulty of obtaining the right real world data into account. So what can we do to bring down the cost of autonomous data collection with a minimal amount of human effort? So to answer this question, we can consider the trade-off between human effort and autonomous data collection as we go from minimal human involvement to complete human involvement. And from this trade-off, it becomes clear that there's a regime in between where a small amount of human involvement provided upfront can significantly bring down the cost of autonomous data collection. And that's the regime we're going to explore today. So we can revisit the standard reinforcement learning paradigm from earlier and change the problem assumptions to allow for a little more supervision to be provided. So if a small amount of human provided data is available to the algorithm upfront, it can potentially serve to guide exploration and make the process of procuring data from the right distribution a lot more directed, safe, and tractable. So the key question to ask in this section is, how do we bootstrap reinforcement learning with prior data in order to efficiently and safely collect the right data in a directed way? Now, it's important to note here that in this problem setting, we're going to assume that the prior data does not just have to be optimal data or demonstration data, but can be arbitrary, potentially suboptimal data or data of mixed quality. So this makes it challenging to apply standard imitation learning algorithms directly to this scenario and requires us to use a more directed scheme to bootstrap from the suboptimal prior data. Now, to bootstrap from arbitrarily provided human data, we can leverage the principle of off-policy reinforcement learning. So what is off-policy reinforcement learning? Off-policy RL is a variant of reinforcement learning where an agent is able to utilize arbitrary prior experience rather than just optimal data or its latest set of collected experience. An off-policy RL does so by using an arbitrary set of experience to assign every state action pair a score, often referred to as a Q function or a Q value. And the idea behind a Q function is really simple. It simply indicates how good a particular action A is when taken at a particular state S in terms of how much reward you expect to accumulate from there. Now, given this type of Q function, leveraging prior data should be really simple. You just pick actions with higher Q values more and choose actions with lower Q values less. Now, this Q value itself is computed by a simple dynamic programming algorithm called the Bellman update. The Bellman update can be understood very intuitively as a procedure for finding the highest rewarding future path through the provided data, starting from the state S and taking the action A. So as shown graphically here, we can see that the Q values are computed backwards recursively via dynamic programming, propagating value from the final state to the particular state S and action A. So in principle, all we should really need to do to bootstrap from this prior data is add human provided data to the set of data collected thus far and run standard off policy reinforcement learning. So this seems great. Seems like a simple formula. It should work. Let's see what happens empirically when we try to do this in practice. We see that this actually performs quite poorly empirically. While most algorithms can start off doing quite okay at 0 steps, they experience a big dip in performance, often destroying the entire benefit of learning from this prior data and performing no better than learning from scratch. So why does this happen? This issue is actually quite subtle and can be attributed to the problem of distribution shift due to incomplete coverage in the prior data. So what do I mean by distribution shift in this context? Now, when a queue function is trained using dynamic programming via the Bellman update on prior data, if there's incomplete coverage over the space of states and actions, then there can be erroneously optimistic queue values at certain states and actions because these state action pairs just didn't exist in the training data and are therefore different than the training set. For these state action pairs, their value is purely determined by function approximation and not actually by training. So these erroneously optimistic Q values, which are indicated by these red circles over here, can be catastrophic for dynamic programming because when you perform dynamic programming with these, it makes the Q values at multiple other states incorrect. This destroys the entire benefit of training on the prior data. All right, so how can we go about limiting this off-policy reinforcement learning algorithm from avoiding propagating these out-of-distribution Q values during dynamic programming? One simple way to avoid propagating these values for out-of-distribution actions is to simply constrain what values are being propagated. So we can just convert our Bellman update into a constrained optimization where we just constrain the difference between the policy and the prior data. So we don't let it actually place weight on anything that is too different. Now working through some algebra, this results in a really simple update, which is just reweighted supervised learning. And intuitively, this makes a lot of sense. It says that the reinforcement learning update is performing weighted supervised learning, where states and actions are sampled from the set of data seen thus far, and then the actions are copied proportional to their exponential Q function, or more particularly, their advantage. So this encourages the policy to choose higher return actions more while discarding lower return actions. And this is great because it matches our intuition, but why does it actually solve these challenges of distribution shift that we just talked about? So if we revisit our graphic from earlier, showing the challenges of distribution shift with standard off-policy reinforcement learning, we can see that our proposed algorithm, which we call awake, avoids the challenges of distribution shift that were alluded to because it actually never allows dynamic programming of anything that wasn't seen before. Since it only does reweighted supervised learning among state action pairs that were already encountered, it doesn't place any likelihood on these out of distribution erroneously optimistic values. And in doing so, it ensures that the Q values are accurate and consistent, retaining the benefits of training on the prior data. Right, so let's try and evaluate some of these ideas experimentally. We can start by considering a special case of this type of algorithm where a small amount of optimal data is provided. And in this case, these types of algorithms enable solving of tasks like object relocation, in-hand repositioning of a pen, and door opening with the 24-degree of freedom hand in simulation. When these tasks are attempted with standard reinforcement learning, it becomes really hard to even solve these tasks at all, or it takes hundreds of hours. Additionally, when you combine this with hierarchical policy representations, this idea can be used to solve long horizon multi-stage manipulation tasks in realistic kitchen environments, which are not even possible to solve with standard reinforcement learning algorithms, even if they take an order of magnitude more samples. So bootstrapping from prior data enables the solving of much harder tasks than we could solve with standard reinforcement learning. We can also consider how learning progresses with suboptimal data. So we can see that qualitatively, the behavior improves significantly more quickly and does better than prior off-policy and on-policy reinforcement learning methods. Quantitatively, we can see that our method, shown in red, is actually the only technique to solve a lot of these tasks in a feasible time frame as compared to a number of offline RL, off-policy RL, and imitation learning methods. So this suggests that a combination of off-policy reinforcement learning and effective prior data is able to significantly improve the RL performance while also being able to utilize suboptimal data. And when applied to real world robotic manipulation problems, we considered two different tasks. We considered opening this white sliding cabinet in a kitchen environment and repositioning this object in the middle of an arena with a four-fingered robotic hand. So we can see that reinforcement learning from scratch often has this undirected, potentially unsafe interaction with the environment. But when you actually bootstrap with prior data using Awake, we can see that the data collection automatically becomes a lot more directed. And within just a few hours of training, we can actually learn these fairly complicated tasks and learn it in a safe and efficient way. We can also pretty easily extend these results to different domains, like manipulation with the three-fingered robotic hand or opening a drawer with a soy robot, which requires careful coordination and accuracy. Okay, so the key point to take away from this section of the talk is that a small amount of prior data can have a massive impact on ensuring that these algorithms are able to collect the right type of data. The work I discussed here shows that reinforcement learning algorithms can go from being limited to simple tasks like 2D pushing in the plane to a much more complex set of tasks and manipulators, as shown here on the right. So the ability to incorporate prior data to have much more directed exploration is critical not just in robotics, but in most domains where exploration can be risky or expensive. So domains like healthcare or autonomous driving are likely to benefit from these types of techniques as well. Okay, so revisiting our ingredients of a real-world RL system, we can provide supervision via data-driven reward design, and we can ensure we're collecting data from the right distributions by bootstrapping from small amounts of prior data with off-policy RL. The last piece of the puzzle we're going to consider involves understanding whether we can actually scale up our systems to ensure we can collect large amounts of data autonomously and keep improving in realistic environments. So to understand the scope of this challenge, let's consider some success of training RL in the real world. So we have here three different systems which are able to learn tasks like object striking, door opening, and opening of a cabinet directly in the real world with reinforcement learning. All right, so this seems great. But if you pull the curtain back on these types of systems, you can see that these systems are far from the promise of plug and play reinforcement learning. In fact, as you can see here, the first work requires a human constantly resetting the puck for a robot to try over and over. And then the second and third work require a specialized reset mechanism which closes the door after every opening attempt. Right? So in fact, most of our current real-world reinforcement learning setups require pretty careful instrumentation, making it very difficult to have these RL algorithms just be dropped into an environment to perform reinforcement learning. So the key question to ask here is, how can we build systems that are closer to this vision of plug-and-play reinforcement learning, where they can collect their own data autonomously without significant instrumentation or intervention? And our solution to this problem thus far has been to say, okay, if the environment and algorithm don't match, then let's just modify the environment till it matches the algorithm. But this feels like the opposite way of thinking about the problem. We always want to operate in the real natural world. We want to modify our algorithms to operate under these conditions instead. So what we need for data-driven reinforcement learning are learning algorithms that can be left to collect their own data and learn with minimal amounts of babysitting or instrumentation. Now, what even makes it necessary for these algorithms to have this type of instrumentation or intervention in the first place? So this goes back to a point we've been making throughout. These algorithms assume access to things that are just difficult to provide in the real world. So for instance, these algorithms assume access to things like low-level estimates of Markovian state, access to reward functions, and access to episodic resets, which keep resetting an environment so you can try over and over again. Now, the discussion in the previous two sections has showed how we can actually learn from raw pixels and obtain rewards from sources like raw videos. But in all of the experiments that we've considered thus far, we've had to either manually construct a complex reset mechanism, or we've had a human in the loop constantly resetting the objects to provide episodic resets. And this seems like a big limiting factor, right? So let's delve into this a little further. So why is this problem of reset-free reinforcement learning even important? It feels like kind of a niche challenge, right? So any autonomous data collection technique will only scale as well as its weakest link. So even if you have autonomous techniques for inferring rewards or learning from video, if you still need a human to be there to constantly provide resets, then it compromises the entire scalability of the data collection pipeline. So we need to develop algorithms that are actually able to operate in the absence of resets. And why is it challenging to operate in the absence of resets? When robots are run reset free, they can get stuck in certain states for really long periods of time. Whereas if you had a reset, the longest this would be for a single episode. But a more subtle challenge here is that if the robot is actually successful and it actually completes the task, pushes the cup to the goal, let's say, the robot will not continue learning since the optimal behavior at that point is to do nothing. And if this happens, then the robot doesn't actually continually improve like we want our RL systems to. So we need to build agents that are actually able to set up their own practice problems. So the question becomes, what should they actually practice on? So to answer this question, it's important to think about what scenarios the robot might actually encounter when it's being evaluated. Right? So in the absence of any explicit indication about what this might be, we can take a pessimistic view on the problem and prepare for the worst. So we can formulate this as a worst case optimization where we say we want to maximize rewards under the worst possible scenario that might be encountered. And working through some simple results, we can see that this results in practicing on a uniform distribution of problems. So you just prepare for the worst by practicing on everything. So for instance, let's say you're trying to put a kettle on the stove, right? And you want to put the kettle on the stove, you have to figure out where to practice from. You want to choose uniformly between practicing from the counter, the fridge, the cabinet, and so on. So to implement this idea of practicing on uniformly random practice problems, we can leverage the idea of learning a perturbation controller. And a perturbation controller is also a learned controller, but it's learned using an exploration objective, which encourages it to visit less seen states. So during training, we can replace the reset phase of our controller with an episode of our perturbation controller, and then train both our policy and our perturbation controller together. So you can think of the perturbation controller as a learned substitute for a reset mechanism. It pushes the robot to a variety of rarely visited states, allowing the robot to attempt the task from a wide variety of configurations. So we demonstrated this system on a couple of real-world tasks. In the task on the top, you have to manipulate the beads of this abacus to a particular configuration. Task on the bottom, you have to rotate this valve to a particular angle. So we start by collecting some indication of what the task is to solve, and then we leave the robot to train for many, many hours, where it's actually learning the policy, the perturbation controller, and the reward model all together. The human is not interrupting the robot during this entire process. And finally, once you've trained this, you can come back, evaluate the robot from a wide variety of configurations, and you find that it's successful on most of them. Now, what's really exciting about this result is that we're able to construct a fully uninstrumented and uninterrupted system that can just be dropped into an environment to learn, as compared to requiring a very specialized setup to learn. Now, a similar system can also be instantiated for the problem of mobile manipulation, where the goal is to use a mobile manipulator to go around picking up trash from dirty rooms, learning both how to navigate and grasp objects. Right, so the resulting training process looks something like this. You navigate around different rooms, picking up and putting down objects, practicing how to get better at both navigation and grasping. And finally, in a new scenario, a new dirty room of a new configuration, the robot goes around the room. It's learned how to both navigate and grasp objects, and learns how to clean up your room. Now, this is nice from a systems perspective, but the actual tasks being solved are still somewhat simplistic. The bottleneck here actually becomes the reset-free learning paradigm itself, and this becomes challenging for single tasks in isolation. However, we rarely actually operate in this isolated single task setting. We usually want to solve multiple different tasks together. So right here, if you're in a kitchen, you don't want to just put the kettle on the stove. You want to open the cabinet, pick up the kettle, close the cabinet, and so on. So the question is reset-free reinforcement learning actually easier with multiple different tasks? So to make the autonomous data collection problem easier in the multitask setting, the key idea we can leverage is that when multiple tasks are being learned together, some tasks can serve as resets for others during training. This makes the whole process significantly easier. So for instance, let's say a robot is trying to put a kettle on the stove, but it accidentally drops the kettle. If you just learn the task of picking up the kettle and putting it back on the counter in sequence, then this automatically provides a reset for the task of putting the kettle onto the stove. So by appropriately sequencing the tasks one after the other, we can put the environment into states where learning all of the tasks becomes easier. What's really exciting about this paradigm is that we can actually learn how to perform complex dexterous manipulation tasks in the real world using this kind of paradigm without human intervention. So we can learn how to perform in-hand manipulation with this four-fingered robotic hand. So the goal is to pick up this object and manipulate it to a particular configuration in the hand by using the fingers in a fine-grained motion. So when the agent starts, the object is in the hand, but it quickly falls out. Then we can try and learn how to recenter the object, which starts to provide resets for picking it up. Once you're able to pick it up, this starts to provide resets for flipping it back over. And this finally allows you to practice doing in-hand manipulation again. After this entire training procedure, which is around 70 hours without any human intervention at all, we're actually able to learn how to do this task pretty well, learning how to pick up an object and then do fine-grained motion. What's really cool about the system is we're able to have a system that learns for an extremely long period of time without any humans involved at all. Now, let's skip this for the sake of time. Now, this is exciting from the perspective of actually enabling our robots to train for long periods, but it still doesn't really answer the question of how do we know what to practice? Right? How do we know which task comes after which other task? So in this framework of reset-free reinforcement learning that we just discussed on the hand tasks, we assume the access to a hand-defined state machine which tells you which task should be executed after which other task. However, when we consider really scaling up robotics, we're going to scale to a large number of tasks and complex interaction between tasks. So we have to move from hand coding to a more data-driven approach to reset-free learning. So one idea that can be quite powerful here is to borrow some ideas from section 2, where we discussed reinforcement learning bootstrapped with prior data. So in that section, we were largely thinking about how this prior data can bootstrap policy learning and how we can more quickly and efficiently collect data. However, a similar set of ideas can actually be leveraged to bootstrap autonomous practicing as well. So in particular, given a small amount of human provided data upfront, we can bootstrap not just the policies for different tasks with an algorithm like Awake, but also the mechanism by which different tasks are practiced one after the other as well. So given some demonstration data of humans performing different tasks as shown here, we can infer how different tasks transition to each other, build a model of the world, and use this to command which task comes after which other task. To evaluate this experimentally, we actually just went ahead and built an entire kitchen. So as we can see here, we have a kitchen with different elements, and we can actually train reset free in this kitchen where we try and manipulate different elements by manipulating or by commanding different tasks. Right, so we actually train in this way for around 60 hours with only very mild resets required every few hours. And finally, we can evaluate this learned behavior on a set of long horizon manipulation tasks where we can actually solve multi-step tasks as shown here on the bottom right. So in this way, we've built a system that can use a small amount of human data to bootstrap both policy learning and autonomous practicing. So the key idea to take away in this section is that learning systems require automation of every component to truly scale. The algorithms for uninstrumented and uninterrupted learning we discussed today help us move from settings like this with all of this human intervention to settings like this, where you can just drop a robot into an environment and have it learn. So this completes the third piece of the puzzle. Through a combination of data-driven reward design, bootstrapping from prior data, and instrumentation-free reinforcement learning, we're able to bridge the mismatch between the assumptions that these algorithms typically make and what's actually available in the real world. So taking a step back, let's think about what all of these techniques serve to accomplish as a whole. These techniques are able to move RL algorithms out of simulation, out of simple video games, to much more complex behaviors in the real world with easily scalable supervision, efficiently collected data distributions, and large-scale continual data collection. And this brings us significantly closer to this vision of plug-and-play reinforcement learning. I think it's important to place into context some of the limitations of this work. So while these advancements provide us the potential to actually train in truly real-world environments, they have been considering somewhat controlled problem settings so far. They haven't been applied in someone's messy living room, for instance, so you don't have much of the mess and human involvement that you might expect there. So while more work does have to be done to accomplish this outcome, as I'll briefly allude to next, the research I described today has taken a really significant and crucial step towards this goal. So what comes next? So as I alluded to earlier, we've started to deploy things into real world environments, but we need to take this to its logical extreme. Right? So we need to go and take a low cost robotic platform, deploy it in someone's real home around their mess and around all of the unstructuredness of the real world and have it learn over many, many months with messy real world data. Right? So this is going to expose our learning algorithms to not just more interesting applications, but also more interesting types of data. So for instance, let's say you're in someone's messy living room. Some things are fundamentally different, right? So you're not operating in an isolated setting, you're going to have humans around you. So you have to be human-centric in your reasoning. Secondly, you're not going to be solving single tasks in isolation, but you're going to be solving multiple different tasks one after the other. And lastly, you're likely to encounter a much greater physical and visual diversity than anything you've seen thus far. And so in, over the next 5 to 6 years, I want to put a robot in somebody's home, and actually tackle these challenges head on. Okay, with that, I'd like to thank my many excellent collaborators who really did most of this work. These are some of the papers I covered today.